Can you see the screen? Yes, anyone, can you
Yes,
tell
sir.
me? Okay.
Yes, sir.
Yeah, once again, somebody is joining. Just wait. Okay, so we were discussing about the pressure part in the last class, and I told you I have taught this part in the basic mechanical engineering course also, and you can go back to that particular lecture. It could be lecture number 1 or 2. Okay, so this is already known to you. Now I am going to the measurement of pressure. Okay, so the basic purpose of uh, means measurement of pressure is to find out what is the value of the pressure, and there are two types of the devices which we are mainly using. One is the manometers and other is the mechanical gauges. Now mechanical gauges, when we say uh, it's given here, there are different types of the mechanical gauges like diaphragm pressure gauge, dead weight pressure gauge, Bourdon tube pressure gauge, bellows pressure gauge. Okay, so these are some of the devices, so you need not to worry about their names actually, because I am not going to discuss about their constructional features. Mainly we will be focusing only on the manometer part. Okay, which is much more important uh, in this particular course. Mechanical gauges, for example, if you have your if you have bikes or cars or something like that, any vehicle at your home, then whenever you go to the petrol station or petrol pumps, you get the air filled in the tires. So there, the person who is filling the air in the tire has a gauge in his hand, and that actually shows the pressure which is there inside the tire. Okay, so those are the basically mechanical gauges, and they can be of different types. So we are not going into much detail what type is used for what purpose actually. Okay, but I am going to talk about the manometers. Manometers are defined as the devices used for measuring the pressure at a point in a fluid by balancing the column of fluid by same or another column of a fluid. They are classified as simple manometers and differential manometers. Our focus will here be on simple manometers. So we will be discussing something about simple manometers. And don't worry about this details which I just read about the manometers. Okay. When I will be explaining it with the help of the diagram, you would be able to understand it. So once again, from simple manometers, you can come to this topic. A simple manometer consists of a glass tube having one of its ends connected to a point where pressure is to be measured and other end remains open to the atmosphere. Okay, so wait for a minute, somebody wants to join. So simple manometers are basically are of three types. First one is the piezometer, the second one is the U-tube manometer, and the third one is the single column manometer. So we will talk about these three. So this is a piezometer actually. Now you just try to just see this diagram here, which is shown. See here we have a this is a pipeline. Okay. This is a pipeline which is carrying some fluid here. This is the fluid inside it. Okay, and I can say that its pressure. Okay, its pressure at point number A is greater than P atmospheric. Okay, so you know the atmospheric pressure value is 1.01325 bar, or I can say it is 760 millimeter of mercury column. Okay, so I can say that the pressure at point number A is more than the atmospheric pressure. So let us say that the pressure at point A is I will say that say 1.08, let us say this much bar. So it's not much higher than the atmospheric pressure. So what I can do is I can have a sort of tube. Okay, the tube which you can see it here. This is attached to the center, to the pipe actually, to the pipe. Now this fluid which is flowing inside this pipe, this is the pipe actually. So the fluid is flowing inside it. Okay. So what will happen? Because the pressure which is exerted here at the top of the open end of the pipe, this pressure is P atmospheric, and the pressure inside the pipe, which is PA, it is higher than, which is written here also, PA is higher than atmospheric pressure. So what will happen? The fluid level will rise in the tube actually. Okay, so this is the center line of the pipe actually. So the fluid will rise up to a certain pressure, up to a certain height actually, which is shown here by H. Okay, and this H is actually the pressure head of the fluid. What is this H? Pressure, it is the, you can say, the height of the liquid, say water, is H in piezometer tube. Then the pressure at A. So how to measure the pressure at A? See, yesterday in the last class, I talked about the hydrostatic law. Okay, I talked about the hydrostatic law, and I said that pressure at any point is given as rho g z actually. Okay, and z is nothing but this is the height of the liquid above a certain point actually. So here in this case, this is the point, center line of the pipe, where we want to measure the pressure. Okay, and the height of the liquid above this particular line is H. So the value of Z is H here. So the pressure, which is basically, it is the gauge pressure only. It is the gauge pressure at point number A. That value will be equal to rho G into H, and rho g, you know, is the weight density, so small w divided multiplied by H. So this is the value of the gauge pressure. Okay, so uh, basically piezometer, as you can read it from here, is the simplest form of manometer used for measuring gauge pressure. So we are only measuring the gauge pressure. Okay, if we want to calculate the total pressure at point A, then what will happen? Total pressure at point A will be equal to P gauge at point A plus P atmospheric. So the value will be equal to rho G H plus P atmospheric. Okay. So rho G H is the value of gauge pressure at point number A. So gauge pressure at point number A is rho G H, and this PA is the total pressure, or I will say that it is the PA means here it is the absolute pressure. Okay, it is the absolute pressure at point A. So absolute pressure is gauge pressure plus atmospheric pressure. So I hope this point is clear to you. So let us move to the next point. Now this, as you can see here, see in this case, I said that the pressure, I have considered a particular value of the pressure at point number A as 1.08 bar. So it's a very small pressure. This pressure is the total pressure actually. Okay, this is the total pressure. So this is not very large value. Okay, so what I can do is I can say that this piezometer tube or piezometer is used for measuring of very small gauge pressures, very small values of the gauge pressure. But suppose if the pressure in the pipe is very high, then what we will do? Then we can go for a U-tube manometer. Okay, what is a U-tube manometer? See, U-tube manometer is a pipe which contains a heavier fluid actually. So what you can see here is, here there is a pipe. Okay, and let us say the pressure at point B, and I'm talking about the absolute pressure here in the pipe B. Let us say this is 2 bar. Okay, this is a quite high pressure, because if I would like to calculate the gauge pressure at point B in the pipe, that would be equal to PB minus P atmospheric. And if I say that the total pressure or the absolute pressure at point B is 2 bar, So I will have to subtract the atmospheric pressure. So I can say it is approximately equal to 1 bar gauge pressure. So it's a quite high value of the gauge pressure. And suppose the fluid which is flowing here is water only. So what is the height of the water column that would be required actually. Now I will tell you. For example, um, if I have to measure the atmospheric pressure with the help of mercury column, okay, if I take the mercury column, and that I said that 760 millimeter of mercury column is equal to 1 atmosphere. Now that means I will be requiring a pipe or tube in which whose height is somewhere around, let us say, it is 76 centimeter for the measurement of the atmospheric pressure. Rather, we will be requiring a larger height so that the mercury doesn't spills over outside, uh, out of the tube actually. Okay, so we can say that we will be requiring a length of pipeline tube which is around 1 meter actually. Okay, but suppose if I want to know how much should be the length of the pipe if I am using water as the fluid for the measurement of the atmospheric pressure. Okay, so I can say that if I take 1 bar as the pressure, then I put rho g h, because this is the value of pressure P. Okay, and now let us try to find out. I will write 1 into 10 raised to power 5, this much Newton per meter square. This is the atmospheric pressure value. Rho. Rho for water is 1000 multiplied by value of G, 9.81 multiplied by H. So this is the column of water that I would like to calculate. So if you will calculate the column of water, that will come out to be 1000050 divided by, I can say that this total value 1000 into 9.81 is, let us say, 10000. So approximately I will be needing a pipe of height 10 meters. So this 10 meters will represent a height of means a pressure of 1 bar. So it's a quite huge length of the pipe, and it's really would be very difficult to measure the pressure using water as a fluid and keeping a height of around 10 meters for the pipeline. So what we do, suppose if there is a pipeline that, like I am talking about this point number B, I'm talking here in this pipeline. I am saying that the water pressure is 2 bar. I told you it is the absolute pressure, and the gauge pressure is around 1 bar. So if I have to use a piezometer tube, you can understand I will be requiring a length of 10 meters or maybe even more. So I won't be using a piezometer tube. What I will do, I will use a U-tube manometer. You can see this is the construction of the U-tube manometer. It is in the form of two limbs. The left, this is the left limb, okay, and it is the right limb. And uh, uh, here, the fluid which we are using is mercury. Okay, this is mercury. So what we will do, when we attach this manometer, basically the manometer pipe starts from this particular location and it goes like this. Okay, it goes like this. So when we will attach this pipeline to this bigger pipe, the pressure will be exerted from the fluid onto the mercury here. Okay, onto the mercury here. So what will happen, in the right limb the level of mercury will rise. Okay, the level of mercury will rise. Actually what exactly happens is, let me tell you, I will explain it here. For example, if this is the U tube, okay, and if it is open from both the ends, then the level of the mercury would be like this. This is mercury. Okay, this is mercury, and in both the sides the level is same. Now what we do, we attach it to the pipe here like this. Okay, when I attach it like this, the pressure will be exerted here, and actually this side the level will drop down to this particular point from here, and here it will increase by the equal level actually. Okay, now suppose uh, this height from the center here is h1, and this increase in the height of the mercury column on the right hand side is, let us say, yeah, I will measure it now with respect to this particular point because the mercury was initially here. Let me show you once again uh, from the red color. Initially the mercury was here when we have not connected the pipe. The column was here actually in both the column AA, and then when we attach this pipe, because the pressure is being exerted here because of the fluid which is flowing in this pipe, so the level of the mercury falls to this particular location, to particular location B. And here also, if I say this is point B, so from here the level goes up to this particular point. Okay, so this much it increases. So now what we can do is we can equate the pressure at point B actually, because the pressure at point B will be same. So I can say pressure at point B in left limb will be equal to pressure at point, I will call, let us say this is B1 and this is B2 at point B2. Okay, this is B1, and B1 and B2 they are at the same level actually. So I want to calculate the pressure at point B1. So that would be equal to pressure at point B. Where is point B? Point B is here. Okay, point B is here. Plus, now what is the height of the liquid here? From here to here, this height is h1, and the fluid is, let us say the density of the fluid which is here is rho. So it will be rho g into h1. Okay, rho into g into h1. So that is the pressure at point B1, and in the right side the pressure will be equal to, it will be equal to rho for the mercury or whatever the fluid which you are using, multiplied by g, multiplied by, let us say this is h2, this height is h2. Okay, so that is how we can calculate the value of pb. Pb will be equal to, uh, this is rho of the mercury into g into h2 minus this is rho of the, I can say this is rho of the fluid in the pipe, so rho p, this is pipe. Okay, multiplied by g into h1. So I would be able to get the value of this particular pressure pb using this particular equation. Okay, is it clear to you? Is it clear? Okay,
Yes, I
okay.
Yes,
So
yes.
what I will, okay, now I will take the other case. In the other case, what I am considering is, now I want to measure the vacuum pressure. Okay, so if I have to measure the vacuum pressure now, so that means this is the pipe in which the fluid is at a pressure which is lower than the atmospheric pressure. I will call this as the point B. Okay, and I will connect, now initially, now let us see it here. This is the manometer here. Okay, I am trying to show it here. I have not connected it. Yeah, this is the manometer here, and initially the mercury level in both the sides is same. Okay, because it is open. to the atmosphere. So the level of the mercury in both sides is same. Now what happens, because the pressure here at point B is now less than atmospheric pressure. Okay, it is less than atmospheric pressure. The moment I connect it here, okay, because the pressure here is lower, the pressure will be exerted from the atmosphere. So atmosphere will exert its pressure here. Okay, this is P atmospheric. So level in the right limb will fall. So let us say that the level in the right limb falls to this particular point. Okay, and here it rises up to this particular level. Okay, so this is the location where this on the both sides the manometer is means this is now mercury up to this particular point here. So I will call this point as, let us say, A, this is A2, and this is A1. Okay, and here we have the that particular fluid for which we have to measure the vacuum pressure actually. And let me call this height as H1, and from the center line this height is H2. Okay, now at point A1 and A2 the pressure is same. Okay, at A2 it is the atmospheric pressure. So I will write the equation, pressure in left limb at A1 is equal to pressure in right limb at A2. Now, okay, so left limb, I am starting from this particular position. So the fluid which is flowing in the pipe is up to this particular location. So I will write PB. PB is the pressure at point B plus rho of the fluid in the pipe multiplied by G into H2. Okay, plus then it is the fluid in the manometer is mercury. So I will say it is rho mercury into G into H1. And on the right hand side, what is the pressure which is acting at point A? It is the atmospheric pressure. So the value of the atmospheric pressure is not to be considered, because with the help of the manometers we are measuring the gauge pressure. So right side I will write it is 0. Okay, it is 0. So I can say that pressure at point B is equal to minus rho P into G into H2 minus rho of mercury into G into H1. Okay, so you can see it here. This is the expression which has been derived here. Okay, so that is how we can calculate the value of uh, vacuum pressure in case of manometer. Okay, so let us proceed. Once again, it is the same slide which is shown here, so no need to worry about it. So these are two questions I will discuss. This is the question on for the measurement of the gauge pressure, because in this case it has been considered to be more. I will take one question which is related to the vacuum pressure. So let us see it here. This question, what you can do, I have sent you the notes on the group. You can see this problem number. It is problem number 2.9. So you can go through this problem. If you feel there is any difficulty in understanding, you can bring it to my notice and then I can explain it to you. Okay, but I feel that it's quite easy and you can easily understand it. So I am going for this particular numerical problem. So you can read it here. A simple U-tube manometer containing mercury is connected to a pipe in which a fluid of specific gravity 0.8. So here we have a fluid for which the specific gravity is 0.8. So its density will be equal to specific gravity into density of water, and it is 0.8 into density of water is 1000, so it will be equal to 800 kgs per meter cube. So that is the value. Okay, so here you can see the density of the fluid is written directly, rho1 is equal to 800. So I can also say that the fluid which is there in the pipeline is fluid number 1 actually. So we can use the subscript 1 here with the rho. Having vacuum pressure is flowing. So there is a vacuum pressure. So means it is less than the atmospheric pressure. Okay. So uh, the other end of the manometer is open to the atmosphere. Find the vacuum pressure in the pipe if the difference of mercury level in the two limbs is 40 centimeters. So basically, as I told you, here the pressure which is acting, this pressure which is acting here is P atmospheric. Okay, and this height up to this particular point, this is the mercury actually shown by the pink color. This is mercury, and here the dotted lines which are shown here, this shows the fluid 1. This is fluid 1, and the height of the fluid in the left limb from the center of the pipe is 15 centimeter below. So this is the center of the pipe at this particular point, and its height is 15 centimeter below the center line. So we just have to apply the um, pressure value at this particular point, at point number AA. So if you see in the right side limb, the pressure at point A, is there any fluid above it? Yes, air is there, but normally the pressure that which is exerted because of the air is only atmospheric pressure, and this manometers we are used for measuring either gauge or vacuum pressure, so we don't consider that. That is a sort of reference for us. Okay, so right side the pressure you can always write 0, and what we have to calculate, they have considered that the pressure at this particular point is P in the book, so this pressure is written as P here. Then let us call this as the I can say this is H1 and this is H2. Okay, depends what they have. I don't know what they have considered. H2, yeah, H2 is 40 centimeter, and H1 they have considered as 15 centimeter, which is 0.15 meter. So I can say rho2 G H2. So it is for mercury actually. So it is for the mercury, and this value is for the fluid. Okay, so we know the value of the density of the mercury. So specific gravity for mercury is 13.6. It is not given in the question, but we can always consider it. So the value of the density of the mercury is 13.6 into 1000. So this I have explained you earlier. So the pressure will come out to be this value. So you can see this comes out to be minus 54,543.6 Newton per meter square, and uh, we can also say that it is this much pascals, but here they have written it in Newton per centimeter square. So I will not advise to you to use this particular units actually. So better would be that you go directly for pascal, or you can convert it into bar by writing minus 0.54 436, this much bar. Okay, so that would be better. I think somebody wants to join, so just wait for a minute. Just wait. My PowerPoint is not responding. Yeah, yeah, just a minute. Okay, okay. Yeah. Now we are proceeding to the next chapter. It is on the kinematics of the flow. Uh, Kinematics is basically when we talk about the motion of the fluid. Okay, okay. We are talking about the motion. Basically, we are interested in calculating the velocity and acceleration. So not much is required in this particular case also. Yes, there are two methods. One is so basically you can see here it is the methods of describing the fluid motion. There are two methods. One is Lagrangian approach and other is Eulerian approach or method. Okay, so in Lagrangian approach, a single fluid particle is followed during its motion and its velocity, acceleration, density, etc. are described. Okay, in case of Eulerian method, the velocity, acceleration, pressure, density, etc. are described at a particular point in the flow field. The Eulerian method is commonly used in fluid mechanics. So it's uh, I will explain you what does it means. Yes, for example, this is some domain of the fluid flow. This is the domain of fluid flow, and if I am saying that there is some particle of the fluid which is here, okay, so and it's moving. Suppose it is moving like this, okay. So what I will do, I am following this particle when it is moving from say its position number 1 to position number 2, and I would like to see what is the change in its properties like velocity, acceleration, density, and pressure, etc. So basically my focus is on a particular particle, okay. But when we talk about a fluid, there can be infinite number of the particles, and if I have to describe the fluid motion, okay, I need to know the velocity, acceleration, pressure, and density, etc. of all infinite number of the fluid particles. Okay, so in the Lagrangian approach becomes very difficult to describe the fluid motion. Rather, what we do is we, if this is the domain in which there is fluid flow, and I choose certain locations. For example, this is the location, one of the location. I call this as S1. There is another location, let us say it is S2. Now what I do, I focus my attention on this particular location and this particular location here on the in the fluid domain. So whichever the fluid particle which passes from position S1 or from position S2, I am calculating the its velocity at these two locations only. Okay, but I can have a number of points in the fluid flow. Okay, like I tell you, we studied about steady flow, first law of thermodynamics. Steady flow we studied. What we assumed a particular control volume, and we were looking for its velocity at inlet, and we were looking at for its velocity and other properties at exit. So it was a Eulerian method of study of the fluid actually. So it is quite easy. But when I am saying that Lagrangian approach, if I have to follow that, then I will have to go for, I have to look the properties of each and every fluid particle, and I will have to follow it wherever it is going. So it's a very difficult approach. So normally we usually go for Eulerian approach for the description of the fluid motion. But not much is there in your course. That is the only definition you should try to understand. Okay. Now let us talk about the various fluid flows. There are fluid flows are classified as, one is steady and unsteady, uniform and non-uniform, laminar and turbulent, compressible and incompressible, rotational and irrotational, one, two, and three dimensional flows. Okay, so I will just like to summarize it here only. I will not go to the next slides where the definitions are given. It's quite easy to understand. See, when I say when I talk about the steady flow, I say, I think I have also described it in the basic thermodynamics class, means earlier classes when I was teaching you uh, about the steady flow. I said when the properties, okay, when the property of the fluid, any property of the fluid is not varying with respect to time. Okay, so T here stands for time. This value is actually equal to 0, then it is a steady flow. So the properties of the fluid are not varying with respect to time. It is the steady flow. And when I say unsteady flow, then I will say that property of the fluid are varying with respect to time. So it is not equal to 0. So that is the difference between the steady and unsteady flow. Then I say that uniform and non-uniform flow. Okay, so what is the difference? Uniform and non-uniform flow. Suppose this is the domain of the fluid flow. Okay, this is the domain of the fluid flow, or okay, and if I at any particular time instant, say at time, let us say if I say it is 2 a.m. okay, right now, and I want to, I actually uh, want to see the properties of fluid at different points, and I find that at this point the velocity is 2 meter per second. At this point the velocity is 2 meter per second. Here the velocity is 2 meter per second. And you take any location of the fluid domain, the velocity is 2 meter per second at 2 a.m. Suppose at some other time, say 2:05 a.m., this velocity changes to 3, this also changes to 3, this also changes to 3. So everywhere throughout the domain of the fluid flow, the property is constant at a particular time instant. So such a flow will be known as the uniform flow. And non-uniform flow means at a particular instant of time at different locations, the value of the velocity may not be same. Okay, so if I say just a minute, if I say this is the fluid domain, and it is, say, let us say 2 p.m., and if I calculate the velocity here, I find out the velocity here, it is 2 meter per second. At same instant of time, at some other location, this is 3, some other location it is 4, some other location it is 5. So such a flow is non-uniform flow. So uniform flow means in the domain of the flow, domain of the fluid, the properties are constant at a particular instant of time. I think I will show you this also. Yeah, this is the space coordinate. So here it is also written velocity with respect to the space coordinate at a particular instant of time. So t is equal to at a particular instant of time. I don't know why it is written. That should be equal to 0. So change in velocity with respect to length of the flow in the direction s, that is equal to 0. In non-uniform flow, del v by del x at a particular time will not be equal to 0. So such a flow will be equal to non-uniform flow. Okay. Then laminar and turbulent. Laminar means, for example, if a fluid is flowing, okay, this is the layer of the fluid. The other layer is also parallel to this layer. There is another layer which is over it. It is also parallel to this layer. Then there is next layer. So the layers are parallel to each other. They are flowing in the properly defined paths. Okay, so such a flow will be known as the laminar flow. So laminar flow is defined as that type of flow in which the fluid particles move along well defined path or streamlines, and all the streamlines are straight and parallel. Thus the particles move in laminas or layers, gliding smoothly over the adjacent layer. This type of flow is called streamline flow or viscous flow or laminar flow. Okay, or laminar flow. Okay, when we talk about the turbulent flow, if the fluid is flowing something like this, okay, like this. So they are, the layers of the fluid are not parallel to one another, they are mixing with each other, then such a flow will be known as the turbulent flow. Okay. So the turbulent flow is that type of flow in which the fluid particles moves in a zigzag way. Due to the movement of the particles in a zigzag way, the eddies formation takes place, which are responsible for high energy loss. So there are certain things which are given here. Also, you can you need not to follow this. Okay, this is not required. Now, compressible and incompressible. Compressible means very simple. Compressible means the flow in which the density of the fluid changes from point to point, or in other words, the density is not constant for the flow fluid. The mathematically for compressible flow, we say density is not constant, and when we say incompressible, we say density is constant. So incompressible flow is that type of flow in which the density is constant for the fluid flow. Liquids are generally incompressible while the gases are compressible. Mathematically for incompressible flow, rho is constant. So it's quite simple. Rotational and irrotational. Rotational means, for example, there is a fluid particles and this is the center of the mass. Okay, I will read it from here. Rotational flow is that type of flow in which the fluid particles, while moving along streamlines, also rotate about their own axis. So, for example, if this is a flow, so fluid is rotating about its center actually. Okay, like this. So it's there is a complete rotation. It's making a complete circular rotation about its center. So such a flow will be known as rotational flow. If they are not moving along their own centers, then that flow will be known as irrotational flow. So if the fluid particles while moving along the streamline, so you can say this is a streamline actually. So we are not going in the definition of the streamline. Do not rotate about their own axis, then this type of flow is known as irrotational flow. One dimensional, two dimensional, and three dimensional flows. So if I say that u is a function of, or some other property is a function of one direction only, means u is changing with it in the x direction only, then I will say it's a one dimensional flow. Whereas the value of v is 0, w is 0. So okay, so velocity is depending on only one direction. Similarly, other properties may also be varying with respect to only in the one direction. So such type of flow will be known as one dimensional flow. If uh, if the properties are varying in two dimensions, for example, like velocity here represented by u is a function of x and y. So x and y are two directions now. So we will say that it's a two-dimensional flow. V is also a function of x and y, and w, which is the velocity in the third direction, that is 0. So basically we are talking about three velocities, u, v, and w. U is the velocity in x direction, v is the velocity in y direction, and w is the velocity in z direction. So three-dimensional means the velocities are depending upon all three coordinates x, y, and z. Okay, so that would be a three-dimensional flow. So now I will tell you something about rate of flow or discharge. See, it's quite simple definition. When I say rate of flow or discharge, it is nothing but it is represented by q. It is equal to area into velocity. Okay, so units are actually, area units is meter square, velocity is meter per second. So it is nothing but it is meter cubes per second. So it is you can also call it as discharge, or you can also call it as volume flow rate. Okay, so anything will suffice. So you can read it from here. It is defined as the quantity of the fluid flow per second through a section of a pipe or a channel. Okay, for an incompressible fluid, the rate of flow or discharge is expressed at the volume of the fluid flowing across the section per second. So it's for the liquids actually. Okay, it is for the liquids. For compressible fluids, the rate of flow is usually expressed as the weight of the fluid flowing across the section. Okay, so weight of fluid or mass of fluid can also be written as uh, uh, Yeah, it's written as weight of the fluid only. So this unit should not be used. You should always use Newton per second. But normally when we talk about the discharge, when we talk about discharge or rate of flow or volume flow rate, you should use this equation: Q is equal to area into velocity. Okay, area into velocity. Then we talk about the continuity equation. Continuity equation means uh,
So,
yes.
and the area, how can I calculate the area? Or
Okay, okay, I will tell you. See, for example, if there is a pipeline, okay, and I am choosing this section as 1 1, this is the section 2 2, okay. So here you may be having, this is a fluid which is flowing through it, and I want to calculate the discharge through this pipe. So I know the diameter of this pipe, okay, it's a circular pipe, so area will be equal to pi by 4 d square. Or suppose if it is a channel, channel means for example if it's a river, or if I say it's a rectangular channel, something like this, I will try to make the sketch. Okay, for example, this is the side view of the channel. Okay, something like this. So if, or you can say it's a rectangular pipe, so I can take the rectangular area of the rectangle, okay, multiplied by the velocity, that will give me the discharge through it. Then continuity equation is nothing but it is known as mass conservation. Mass conservation. Okay, when I say mass conservation, you can see that there is a diagram showing here. This is a diverging pipeline. Okay, fluid flowing through a pipeline. This is section 1, this is section 2. Okay, and this is the direction of the flow. So if I want to calculate the mass at section 1, so mass which is passing through the section 1 should be equal to the mass which is passing through the section 2, and I can say it is also equal to m. So basically continuity means whatever is the mass which is entering from the one side, same mass will be leaving from the other side. So that means there is conservation of mass. So it's a principle of conservation of mass. It is principle of conservation of mass, and it is known as continuity equation. Thus for a fluid flowing through a pipe at all cross sections, the quantity of the fluid per second is constant. Okay, quantity of the fluid means mass of the fluid is constant. So if I have to write at section 1, what is the mass here? I will write rho 1. Rho 1 is the density multiplied by area of the cross section at section 1 multiplied by whatever is the velocity here. So rho 1 A1 V1, and that should be equal to rho 2 A2 and V2. Rho 2 is the density at section 2, A2 is the area of section at 2, and V2 is the velocity at section 2. Now, for example, this is the generalized case actually. Okay, this is the generalized case. Now, what happens, for example, if it is a liquid, okay, then in case of liquid, rho 1 will be equal to rho 2. For example, if we are considering water. So, the effect of pressure on water is very, very less. Okay, and its density will not vary. So in that particular case, we can cancel rho 1 and rho 2 from both the sides. So I can cancel rho 1 and rho 2 when it's liquid. So in case of liquids, I will write A1 V1 is equal to A2 V2. And what is A1 V1? A1 V1 is nothing but it is discharge. So discharge which is entering at point number 1 is equal to discharge which is leaving at point number 2. Okay, because the density is same, so mass is going to remain conserved. So this type of equation is known as continuity equation. And rather see, when I say rho 1 is equal to rho 2, it also means that it's a incompressible fluid. Okay, it's written here, if the fluid is incompressible, then rho 1 is equal to rho 2, and mostly this will happen in only case of liquids actually. So that is why the continuity equation will reduce to a1 v1 is equal to a2 v2. So I think these notes have already been given to you, and you can read those notes. And if you have any problem, you can ask me in the next class. Here, I think there are some numerical problems, and very less course is left now. 3 4 slides more are there. So, okay. So We will discuss that in the next class, and in next class I would like to finish your course for part A actually. And after that, if you will be having any questions, we can discuss that in the further classes. And I have already told you in the group, your examinations will take place after you reach India. Okay, so let's see. Probably from 8th or 9th of March, we can start taking your examinations. Whatever the remaining exams are there, we will take it then.
It
Okay.
will be online or it will be at school.
Yeah, I could not get you. Can you speak loudly?
I said it will be offline or online.
Once you reach here, we will decide. I think most probably it would be online only. Okay, because for offline, I will also have to come to the college, and probably it will means it will depend actually. Let us see what happens. So for the timing, I can't say anything whether it will be offline or online. 99% chances are there it would be online only. Okay,
Okay, sir. Okay, sir. Thank
so
you.
just wait a minute. I will stop the